A leaderboard will not tell you which model is worth paying for. Use a Pareto frontier in Python to compare quality, latency, and cost together. This is the workflow you'll know how to run when we're done, which identifies non-dominated models by comparing quality, latency, and cost. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Many teams pick the top model by accuracy alone, and then wonder why runs are slow and bills are huge. In production, you have to balance three things at once: quality, speed, and predictable cost. A Pareto frontier helps you spot models that aren't dominated on those axes, so you can pick one that matches your latency and budget constraints without losing too much quality. Imagine your usual leaderboard, but with two extra columns: runtime and cost per call. The Pareto frontier highlights rows that are efficient across all three numbers. It won't hand you a single winner. Instead, it gives a tight shortlist and the trade-off story you can act on. We'll build a small pipeline, read a toy evaluation table, compute an efficiency ratio, flag Pareto-efficient models, score and filter them, then apply deployment budgets to get a ship-ready shortlist. A few clear calculations will turn noisy metrics into actionable choices. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. This snippet assembles a compact pandas data frame of evaluation results, so the rest of the workflow has shared context. The dictionary raw captures model names with their measured quality, latency in milliseconds, and unit costs, making every metric explicit for later reuse. Creating DF from that structure yields labeled columns, which keeps calculations reproducible when we start normalizing, slicing, or exporting subsets. Because every downstream calculation references DF by column name, replacing the toy data with fresh evaluation exports requires no extra rewrites or hidden positional assumptions. The printed summary confirms the table loaded 6 models and surfaces the current best quality value. Now that we have a labeled table, we want a simple efficiency metric to compare apples to apples. The next snippet converts units and ranks by a basic ratio. This example turns the shared data frame into a latency-aware efficiency view, so ratios highlight standout models. The new column, Latency S, converts milliseconds to seconds, capturing an interpretable runtime unit for later reporting. Efficiency then divides the observed quality by latency S and cost USD, revealing how much performance we gain per unit of time and spend. Sorting once and taking iLock 0 keeps the winning model visible without mutating the original order, which preserves reproducibility for subsequent steps. iLock, which selects rows by integer position, lets us peek at the top performer. The printed message confirms which model currently leads on efficiency and communicates the actual ratio we can compare against new experiments. Efficiency gives a single number view, but it can miss non-dominated trade-offs. The next code finds models that are not strictly worse than any other across all three metrics. This code tags Pareto-efficient models using a vectorized numpy dominance test to avoid nested Python loops. Converting the relevant columns to a numpy array gives us dense numeric data, so broadcasting comparisons stay fast and deterministic. Inside the loop, the masks identify any row that is at least as good in quality while no worse in latency and cost, while the strict part ensures equality alone is not treated as domination. Appending the negated dominance result builds a Boolean list that matches the data frame row order, making the final assignment trivial. The printed count verifies how many models survive as non-dominated choices. With Pareto flags, you can still prefer higher quality. The next step scores Pareto models with a configurable floor and penalties to choose a practical favorite. This snippet prioritizes Pareto models that meet a minimum quality target before applying latency and cost penalties. The mask isolates rows already marked Pareto-efficient, so the weighted score calculation never touches dominated candidates. The penalty uses df.lock to combine quality with latency and cost terms, producing an interpretable composite that stays proportional to the raw units. Filtering with the quality floor parameter keeps subpar models out of the ranking. Increasing it narrows the shortlist toward only premium quality, while lowering it reintroduces faster or cheaper but weaker options. The printed result names the highest scoring contender and reports the composite score we acted on. Finally, we must respect production budgets. The last snippet applies latency and cost constraints and sorts what remains for a human review. This example adds deployability constraints so the Pareto data produces a shortlist that respects real latency and cost budgets. The new production-ready column requires is Pareto to be true alongside budget checks, ensuring we never promote a dominated or over-budget model. Chaining sort values with weighted score and quality keeps the preferred ordering stable for review logs or dashboards. Tightening the latency budget or cost budget immediately shrinks the list to only the fastest or cheapest items, while relaxing them broadens the set for exploratory comparisons. The printed summary shows the selected model names and total count, signaling which options are safe to ship. In a real project, this maps cleanly to a CI step. You run the evaluations, update the data frame, and then promote models that pass the production-ready filter into a deployment candidate registry. The same checks work for larger collections and automated dashboards. Recap: use a Pareto frontier to find non-dominated models across quality, latency, and cost. It gives you a short list of efficient choices rather than a single automatic winner. Reach for this when accuracy alone would hide slow or expensive options. One caveat: it narrows candidates but still leads the final call to product judgment. Next step: scale this exact pipeline to a larger evaluation batch and add systematic timing and accuracy checks so you test at production scale. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.